Hello and welcome on board. This is Design the Engineering Process, a channel where we give a walk through on process engineering operations and design. Let's dive in. For today's content, we're going to be looking at the 14th equipment on our model palette, which is nothing other than our distillation column. Before we proceed with our distillation column, we're going to be having a very, very important update on our content. We're looking at how we can move ourselves from the current height we are to somewhere a little bit more higher for progress. So stick with us to find out what that content update is. Let's get started. In the 19th century, there was this madly obsessed scientist called Distillation de Collieon. So what exactly was Distillation de Collieon obsessed with? He was obsessed with this idea of eradicating the use of several separators to separate complex mixtures. Simply because he found that idea of the whole several separators separation to be nothing other than waste of time, energy, resources. Distillation de Collieon embarked on a life journey. Well, let me be honest, I'm not really sure if it was a life journey because I wasn't there. But Distillation de Collieon embarked on a journey to find the perfect single entity which could carry out the whole efficient separation of numerous separators combined in a single entity. And this is when Distillation de Collieon came across a particular equipment in our modern day refinery, which we call the distillation column. So this is what a distillation column looks like, in case you did not know. And no, it's not a French baguette. If you're seeing a French baguette, then you're probably hungry, which I also am. That makes two of us. Oh, back to the gist. A distillation column. What exactly is a distillation column? A distillation column is a tall vertical vessel used in process of distillation. Now, what exactly is distillation? A technique employed to separate mixtures based on differences in the boiling points of components. The column contains a series of trays or packings, materials that allow the vapor to rise and condense multiple times, facilitating the separation of various components of the liquid mixture. Types of distillation column include tray or rather plates columns, packed columns. So the tray column is nothing other than a distillation column having trays packed inside the distillation column. And for the packed, it's basically having packings packed inside the distillation column. Like I'm talking about PACK being PACK inside the distillation column. I'm sure that's not that confusing. The third distillation column, continuous distillation column. Continuous distillation column is what most distillation columns are, not all, but most. It basically means it's having a reflux system. It's more like a loop, having a continuous process, and this normally deals with products of large volume, large quantity. Then for the batch, it's like the opposite of the continuous columns. It works in batches. It's not like a continuous process like the continuous column, and it majorly deals with little quantities, little volumes of your substance going inside the column. Then for the azeotropic distillation columns, they deal with substances which tend to form azeotropes or azeotropic characteristics inside the column. Then for the vacuum distillation columns, they carry out the distillation operations at vacuum pressures. And that's it for the types of distillation column. Major components of a distillation column. You have the column shell. That's basically the outer casing of the distillation column, more like the body you can see and touch from the outside. The trays or the packing, like we discussed earlier, the ones inside the distillation column, and their function is to provide a proper surface area for the interaction of the vapor and liquid, where the whole condensation and evaporation distillation process takes place inside. So much English. The reboiler. This is where the reflux action comes in, especially for the continuous continuous distillation column. The reboiler basically boils the liquids that come down as condensates. We will get to make more sense about what I'm saying right now very soon. The reboiler boils the liquids, the remaining liquids that condense back to the distillation column. It boils them back up to do more distillation. For the condenser, it condenses the vapor down to become liquid and go out through the bottom outlets. Too much English. The feed point, basically where the feed goes inside the distillation column. Your product going inside the distillation column, that's that point. And this is a schematics for the distillation column. Like we said, the column shell, this is the outside casing. For the tray/packing, this is it. The white lines, those are basically like the packings, dividing them. This isn't actually how it completely looks. It has a more complex configuration, which you could look up. The feed points where it goes inside the distillation column. Then at the top, we have the condenser, which does the cooling of the vapor to return it down to liquids. And at the bottom, we have a reboiler, which boils back the liquid to send it back to the distillation column to go back up. Then it's basically called the reflux, the reboiler reflux, the quantity, the substance going back inside the distillation column. It's called the reboiler reflux. And for the condenser, the one going back to the condenser reflux. And just at the top here, we have a separator. Now, we have different scenarios for our distillation column, which we get to look at. But for now, let's just naturally stick with this part where we're having two outlets at the top, the overhead vapor and the overhead liquids, which we call distillate. So when you do your whole boiling and it goes up the vapor, you have a condenser. Naturally, when you condense, you expect the whole the condensate, the distillates, to go back inside the distillation column for more distillation action. But then sometimes you're interested in what you might have for the tops, and that's why you have an overhead vapor. This is where you collect your tops, basically the vapors that come out. And at the bottom, sometimes you might be interested in the distillate, the overhead liquids, just beneath the separator here. That's what goes out, and a little proportion of both the overhead vapor and overhead liquids, which is called the distillate, a little proportion goes back into the condenser to do more reflux action to make the process more efficient. So this is basically where the whole secret of combining the series of separators into one entity comes in, what Distillation de Collieon was so obsessed about. A quick note though, you shouldn't share that information about Distillation de Collieon with historians. Not that it's not a true story or anything, but it never came from me. So, reflecting back at the content update that we talked about in the beginning of the content, as you can see on the right hand side of our screen, we have a blue theme which reads Process Engineering Design using Aspen Hysys for Beginners. This particular course, the journey, is the one that we have been embarking on ever since we started this channel, the beginner's journey. And sadly, and not too sadly, today marks the end of the beginner's journey, the beginner's content, basically. And we are going to be rounding it up with today's equipment, 14th equipment, which is the distillation column, as we have already talked about. So, on the left-hand side of the screen, in the red theme, we have Process Engineering Design using Aspen Hysys for intermediates. So, what this basically means is that we're going to be having another class. And what this new class, the intermediate, is going to cover, as the name implies, we're going to be setting new horizons for ourselves. We looked back at the beginner's journey and we have covered nothing more than equipment. We did some little designs, but they were just prior to setting examples to the equipment we were operating. And we wouldn't really call that a hands-on experience for real-life design, process engineering design. But with the intermediate course, we will be looking more in-depth into process engineering design. We're going to be getting ourselves into not so complex designs, basically real-life designs, but they are not too complex, to see how well we can do with the knowledge we gain from the beginner's journey, and we will try and look at some other equipment that we were not able to look at in the beginner's journey. So it's the end of the beginner's journey, but at the same time, the beginning of another journey, more like the beginning of the end or the end of the beginning. I don't know which one sounds better, but the bottom line, we're going to be having another class to expand our horizon, our understanding on the whole process engineering design. But then the most important part, what do you think might happen if you merge the two classes, the beginner's journey that we just had, or we're about to conclude, and then the intermediate that we're about to get into? What do you think might happen if by any chance we conclude both of them? Where do you see yourself as a process engineering designer? Let's see.
歌姫のところにいたやつの気配が消えた。逃げの算段はついてるわけか。仕方ない。少し乱暴しようか。術式順天、青。術式反転、赤。待て、ブラザー！フォード、なんで止める？それ以上進むな。巻き込まれるぞ。挙式紫これでは払えたかどうかもわからん。Yay!
And this right here is the sole purpose, the whole essence of design, the engineering process channel, the professional journey, where we carry out the whole real life, not just the real life, the real life process engineering designs. See what it actually looks like in a real life scenario. Unfortunately, we could not jump directly to this when we started the channel because it's something very, very complex and requires a lot of background knowledge and experience. So we had to go through the pain of we're actually still going through the pain of the beginner's journey and then the one coming up next, the intermediate journey. But believe me, with those two courses, it's going to be more like a scenario of bleed more on the training ground and less on the battlefield. So with this, I believe we're set to conclude our beginner's journey and launch our intermediate journey. With your support and care as always, we're going to go very far in a short period of time. Remember, get greater heights are attained, breaching gaps between reality and design. Let's head to the modeling environment. We're back to the modeling environment. So, as always, the first step is to drop a stream, provided you have selected your paramount component list and fluid package. For the new viewers, if you do not know how to select the component list and the fluid package, as always, the link will be in the description. As a matter of fact, the whole previous content links will always be in the description. So for today, we're going to be working with two components, ethanol and H2O. We're going to be having a mixture of ethanol and a mixture of H2O. And we are going to be working with something slightly different today as a fluid package. We're not going to be going with the traditional Peng-Robinson. We're going to be working with NRTL, non-random two liquids. The reason for this is that Peng-Robinson isn't completely 100% suitable for this type of operation, for separating this mixture. That's why at this point, the whole design is going to be all about research to gather information before you do start the design. And the research goes down to even the most insignificant thing just to make the best out of your process. For today, we're going to be working with the NRTL as the fluid package. That's more suitable for this operation. and then we can go ahead and create our stream. Let's call this ethanol slash H2O. And for the composition, we're going to be working in mass fraction. All right. For the composition, we're going to be having about 30%, 0.3% ethane. That's 30%, and 0.7, which is 70% H2O. With that, we have successfully selected our component list, and then we go back and specify our parameters. We're going to specify temperature. We're going to give it a temperature of about 81 Celsius and a pressure of 1 ATM, 1 atmospheric pressure. And then a mass flow rate, since we are working in mass fraction, we're going to give it a mass flow rate of about 50,000, let's say 50,000 kilogram per hour. And with that, we have successfully created our stream. Now, something very important we need to take note about is that before you carry out the separation of any substance, as we discussed in the previous content, you need to do a research to know what type of process is best for separating a particular mixture. Well, it comes down to what kind of goal you want to achieve in terms of separation for the particular mixture. In our case, it's certain that we're using distillation, but even at that, there are different types of distillation such as crude distillation, fractional distillation, cryogenic distillation, azeotropic distillation. Even though in Aspen Hysys, it's very, very hard to differentiate them, because for almost all of them, you use the normal distillation column that is there. It's not like we have a separate distillation column for vacuum distillation, azeotropic distillation, crude distillation. You use the default distillation column, but then your approach towards that particular process, that particular distillation, would vary for the kind of distillation and the kind of end product you want in your process. But in our case, if in a written case, rather, before we talk about our case, in a written certain fact, the best way to separate ethanol and H2O mixture is by carrying out an azeotropic distillation, where you add a third component into the mixture to do more of absorption of a particular mixture inside a particular component inside the mixture. It's kind of complex. For now, we will do away with that. So we're going to be working with the normal default distillation, a simple distillation. And with a simple distillation, we cannot achieve 100% separation between the two components. That's the ethanol and water. We cannot 100% separate them, but we can hit a purity percentage of 90% and above, hopefully. 90% and above, hopefully. You can hit that, and that's a good benchmark to hit. But then we will do a little bit of optimization, which might be painstaking and time-taking, but it's for the best. We can see what the best purity percentage we can attain for the mixture separation. With that, we can go on. So we're going to be dropping a distillation column, the 14th equipment and our model palette. This is it. That's it. Heads up, the distillation column is one of the most complex equipment in Aspen Hysys to actually work with. So it requires a gentle approach and a lot of research, as we've been saying. Hopefully, as time goes on with experience and knowledge gathered from the content, we will be able to always find a way around dealing with the distillation columns. So at the bottom, like we had in our schematics, we have a reboiler at the bottom. The reboiler that does the reboiler reflux effect of boiling the little liquids at the bottom. So the liquids that we would be having at the bottom of the column would still be a mixture of ethanol and H2O. But then the reboiler does a little bit of reboiling to vaporize one of the two components, so that it can go up and have a more efficient separation. It's a loop, a continuous process. Basically, it continues doing that until we have an efficient separation between the two components. As for the condenser, if by any chance a little bit of the second component follows the first component trying to be separated, the condenser does the condensing to bring it back to the bottom to have a better purity level at the top. So let's be more detailed about it. Ethanol has a boiling point of somewhere around 78 to 81 Celsius, and then at 1 atm, please take notes, at 1 atm pressure, it has a boiling point of 78 to 81 Celsius, whereas for water, through our elementary science, we know that it is 100 Celsius. So with that, we know that ethanol would be evaporating before water. So ethanol is lighter, ethanol would be at the top, and we expect our water to be at the bottom. But in an event where we evaporate, we add too much heat to the operation, we evaporate a lot, a little bit of our water might follow the ethanol to the top because their boiling points are not that far apart. So we would need to take note of the approach for the operation. It's the reason why we cannot attain 100% separation using a normal distillation operation. We need to go for azeotropic to attain a better result. Or for the beginner's journey, like we said, we're going to be sticking with the default, the normal distillation. So double clicking on our column, and this is what the environment of the column looks like. Nothing like any equipment we've ever dealt with. But then, like we said, we're going to be having a gentle approach for this. So starting with the condenser has three settings, three configurations. Like we had for our schematics, we have an overhead vapor outlet stream where the gas goes out, and at the bottom, immediate bottom of the overhead vapor outlet, we have an overhead liquid outlet stream, which is our distillate. So in our case, we need to take note that we're having two components, and we do not need a distillate. We just need a vapor outlet and a liquid outlet. And as such, the distillate would not be required. So for us to do away with the distillate, we're not interested in the overhead liquids. All we have to do is just select the full reflux. So all the distillate goes back into the column to make the whole process more efficient. And if we were interested in the distillate, we would work with the partial configuration. And if we were interested in only the distillate and the bottoms, liquid bottoms and the distillate, we would work with a total condenser configuration. But remember, we're only interested at the tops, the vapor, and the bottoms. So we're going with the full reflux. As for the optional side draws, like it said, it's optional, so we don't really need to work with that now. And then something very, very important to look after is the stages. And the stages is nothing more than the number of packings or number of trays inside a distillation column. It is said without doubt that the higher the number of your stages or your trays or packings, the more efficient your separation is. But for me, I like to work with the default configuration, which comes with 10 stages. It does the work for me most times. It's easier to operate the column at that condition, so I normally work with 10 stages, but then in some cases you might need to increase or reduce. So it's more of a research thing. Like we were saying. Now, what we have here is the inlet streams. This is the feed point where it goes inside the column. And as always, we have our inlets on ground. We add them. And then something next to our inlet stream after being added is the inlet stage. It means that what tray does the inlet go inside the column. On default, it's on the 5th tray, maybe somewhere around here. And then that works perfectly fine. But then remember, we said it's a thing of research. For a more efficient separation, you tend to do more research to know what works more for your process to make it more efficient. But we could just stick with the 5th stage. That would do the work for us. And then, like always, we need to label our outlets. We are going to be calling this ethanol because we expect ethanol at the top. It's lighter and it has a lower boiling point. And for the bottoms, we're expecting H2O. at the bottom, liquid H2O. And then just like our heaters and coolers, the condenser and the reboiler act the same way. The reboiler, it's more like a heater, and the condenser is more like a cooler. And as such, they require energy streams. So we will be calling this E reboiler. And then for the condenser, we will be calling this E condenser. And the moment I hit OK on that, after labeling everything, you have a new option at the bottom, next, telling us we're good to go. As you can see, we have 1 out of 5 pages, so it's not like any other equipment. In most equipment, all we have to do is at the inlets and outlets, some cases, energy stream, and then we specify a particular parameter in our worksheet. But then for distillation column, we have extra about 5 things we need to do before we can even actually operate the distillation column. So that's why we say it's one of the most complex. But then we will work around it. We will find a way to deal with that. So for the reboiler, we have 3 configurations. But before that, let's look at the types of reboilers. Regular Hysys reboiler, the one we already have, we've seen. The heater, if in case we want to use a heater in place of the reboiler and the heater are much more similar. But then in some cases, the reboiler is more like a heat exchanger than a heater. But then in Aspen Hysys, it acts more like a heater, the reboiler. So a heater and the reboiler wouldn't be far apart. And then the heat exchanger, in case you want to use a heat exchanger, meaning that you would have to add an extra stream that goes through the tube or the shell, and your product's going through either the tube or the shell. So the heat exchanger, in case you want to use the heat exchanger, you could select that, but let's work with the default reboiler. That would do the work. And then for the reboiler configuration, we have once through. It's just basically talking about the reflux, how the reflux action happens, how you want it to go back. Once through, it simply goes back in and up and does the separation, and then circulation without baffle. The baffle is nothing more than a little nudge inside the distillation column. It's more like the wear in our separator, the wear that separates the heavy liquid boundary and the light liquid boundary inside our horizontal 3-phase separator to avoid them from mixing. But in this case, the baffle is the nudge inside that does a little primary separation before the main distillation separation technique takes place for our mixture. So in an event where we send in our mixture, our feed inside, for our case, we're probably having liquid. It's liquid, completely liquid. So a heads up is that you're supposed to do a research for even the most suitable vapor fraction to carry out that distillation process you want to achieve. In our case, we're having liquid, so it wouldn't really matter that much. And even in Aspen Hysys, even if you're having a mixture, it wouldn't really matter that much. But in real life scenarios, in an event where you're having a mixture, you use the baffle configuration. So when the mixture hits the baffle before going down to the bottom of the column, it does a primary separation, making a turbulence between the mixture to separate the gas from the liquid, instead of the whole gas being trapped in the liquid and going down to the bottom to start the whole distillation process from scratch. So the baffle does a little separation, separating the gas from the liquid, and some of the gas go to the top and some of the liquids with little bit of vapor in them go to the bottom. So that's what it is. But without circulation, meaning it doesn't do a reflux action, a heavy reflux action. Then with circulation with baffle, it means it has a baffle and it does a complete complex reflux action. But for us, we're working with the defaults, which is the once through a simple reflux, and does a separation for us. So with that, we've covered this page, the second page. Next, we have to specify condenser pressure drop, reboiler pressure. Remember, we're working at 1 atmospheric pressure. In our case, for the beginner's journey, let's just work with a constant pressure drop, meaning it doesn't change. We're going to be working with 0 pressure drop, no pressure drop. So ordinarily, it's not supposed to be like that. We're supposed to be having a pressure drop inside some equipment, but for the beginner's journey, let's just work without pressure drop. So let's leave the pressure drop as 0 and specify our pressure as 1 atm. And next, for the 4th page, we're having optional condenser temperature estimate, optional top stage temperature estimate, optional reboiler temperature estimate. Like it says, it's optional, but in a situation where you want a more efficient separation, you could just plug in the temperature, but you need to be very careful. Plugging in even the slightest bit of wrong temperature might mess up your distillation process, and that would be headache. That would be a very hard thing to deal with. So in my case, I always allow Aspen Hysys to select the pressure for me, the operating pressure. I leave that blank since it's optional, like it says. Next, we have the vapor rate and the reflux ratio. What the vapor rate means is nothing more than the quantity of vapor, the volume of vapor you're expecting, the flow rate of vapor you're expecting at the top for the vapor. Remember, we are working with 50,000 kilogram per hour, working in mass fraction. So the flow basis here allows us to select the basis. We're working with mass, and the vapor rate it's expecting us to specify how much of the vapor we want at the top. We're having 50,000, so if we select 25,000 here, then we expect the other 25,000 to be at the bottom for the liquids. So let's just specify 25. Let's specify 25,000 kilogram per hour. And the reflux ratio, this is the rate at which we have a reflux action for our condenser and our reboiler. And it's usually between 1.5 to 2. I normally stick with 1.5, the lower end. 1.5 does the work for me, most cases. So 1.5, and with that, we are on page 5 of 5. Now we're good to go. So all we have to do is click done after entering all those parameters. And after specifying the distillation column configuration from page 1 to page 5, we're down to this new tab where we select our design parameters and other things, or rather where we can make alterations, because we already came across something similar to this across our page 1 to page 5 for the distillation column configuration. And as you can see, we're having a red message at the bottom saying unconverged, meaning we have not successfully operated our column. Remember, all we just did was selecting the parameters, the configuration for the column, but we have not operated it yet. And to operate it, all we have to do is click on run. As you can see in the modeling environment, it's having a yellow outline around the equipment, meaning we have not successfully operated it. And to operate it, all we have to do is just click on run. And then the column successfully operates. We have an green message now, you're converged. And as you can see, the column has successfully operated. Our energy streams, and then ethanol at the top, because we are only interested in the overall vapor outlets. If we're interested in distillate, we would have had another stream beneath our ethanol, but we're just interested in the tops and the bottoms, not without the distillate. So ethanol and H2. So now we have successfully operated our column, but then we have to check the separation efficiency to see how much of the ethanol we're able to separate from the H2. And to do that, we double click on our ethanol and go inside the stream to see what it looks like. Of course, it's a vapor, so it has a vapor fraction of 1, and as you can see, the temperature changed from 81 Celsius, I believe, to 88.9. That was Aspen Hysys after an iteration. Remember, we did not specify temperature, so Aspen Hysys automatically found the temperature suitable to do the separation at our given parameters, given conditions that we specified for the column. It's still at 1 atm because we do not specify a change in pressure. So then you need to take note of something very, very important. Our vapor fraction, the vapor rate that was specified 25,000 kilogram per hour as a vapor rate. That's basically the flow rate we expect for the vapor, and that's what we have reflecting in our vapor. So it matches, and then we head to the composition, the moment of truth, to know how much we are able to separate. Wow. With our current temperature and pressure, which was given by Aspen Hysys. Actually, we specified the pressure, but then Aspen Hysys gave us the temperature and we specified the vapor rate, that's the vapor fraction. we have 60% ethanol at the ethanol stream, inside the ethanol stream, and then 40% H2O, meaning we did a lot of evaporation to the point where some of the water followed us at the top. You have 60% ethanol at the top, 60% purity, and 40% ethanol. 40% H2O rather at the top together with the ethanol. So we need to do something about that. But let's look at the purity of the H2O. That's the bottom liquid. As you can see, it's a liquid, 0 vapor fraction, and it's at a temperature of 100 C, 1 atm. Just at the boiling point. Then let's see what we have for the composition. And it also has a 25,000 kilogram per hour mass flow rate, because we had a total of 50,000. If we have 25 at the top, we expect 25 at the bottom. Obeying continuity equation, what goes in equals what goes out, provided there are no losses or accumulation. And then composition, we have 100% H2O purity, 100% H2O purity. Wow. So we basically have 100%, but then we have a purity of 100%, but that does not mean we have completely separated them. To know whether we have completely separated them, we will have to check the recovery rate to know how much out of the total volume of the two components, how much of total volume we have in a particular outlet. In our case, the liquid outlet and the vapor outlet. So we cannot use the mass fractions or the mole fractions to know the exact amount of the volume rather, or the quantity of a component we have inside the stream. It's a little bit more complex than that, but then we will look at that. For now, we have a problem on decks. We have a problem at hand. We need to do something to make sure that this 40% of H2O is reduced. Remember, we cannot attain 100% purity with the normal distillation operation, but then we can hit somewhere around 88, 89, 90, 91. Let's just confirm that with optimization. And to do that, we will be going back inside the column, double click, and then we head to specs. We are currently on design tab, and then you have specs on the left hand side. You click on specs. Ordinarily, to bring down to improve the purity level, we would have to alter the distillation operation. And to do that, it banks on the boiling points. And what relates the boiling point of what brings the relationship about the boiling point of a component or two components or more components is majorly about heat. If you talk about boiling point temperature, it's relating down to heating or cooling. But then in our case, we do not specify the temperature, and we do not have heaters. We do have a heater, which is the reboiler doing the heating, but then we cannot alter the reboiler because we did not specify the temperature. And that's why we're currently on specs. We will be altering what we specified ourselves, which is the vapor rate. Basically, the amount of vapor we have at the top. And to do that, we just need to head to specs, which we are currently on, and look for a specification, a column specification that says overhead vapor or vapor rate or overhead vapor rate. In our case, we do not have that. What we have is a vent rate. So any of the three works: overhead vapor rate, or vent rate. They are basically talking about the same thing. Aspen Hysys wakes up different days, different names. So vapor rate, after double clicking, you can see the spec value basically for the vent rate, overhead vapor rate that we specified inside the column configuration. And all we need to do is just alter that particular value, raise it, make it higher or lower to achieve a better separation. But remember what we said after entering inside the stream: the mass fraction or the mole fraction doesn't specify the amount. It only specifies the, when I say concentration, the percentage of composition in terms of composition present inside, but not the quantity. To do the quantity, there is a certain formula you can use, but for the beginner's journey, we don't really need to do that. And luckily for us, we're working with very advanced equipment that was figured out by our Italian scientist, Distillation de Collieon. Thank you very much. We are grateful. All we have to do is just, let's bring this down here. All we have to do is just head to performance, because the equipment is a very advanced one. All we have to do is head to performance and select recovery, which we're currently on. We're currently on recovery, and then remember the bases you're working with. We're working with mass bases, and select mass, and then under here we have products and we have feeds, and this right here will be telling you the amount, the quantity of every product you have inside another product. So it's basically going to be telling us about the quantity that we need to know, and we're going to be using the quantity to know the purity percentage. We're currently at a vapor rate of about 25,000 kilogram per hour, and with that we have a purity level of 100% ethanol. And okay, we're looking at it the other way around. This is a column and this is a column. Column for ethanol, column for H2O, and then a row for ethanol, row for H2O. We look at it from the row side and not the column side. So ethanol percentage, we have 100% ethanol and 0% H2O. That's what we have in terms of recovery, the quantity we have. So remember, in our ethanol, we were having 40% mass fraction. This was only the mass fraction, but not in terms of quantity to purity. This right here tells us about the purity, and then it's telling us that we were able to recover 100% of the ethanol completely. We recovered all the ethanol, but then we have a little bit of water inside. And then whereas for the H2O, we have 28%, 28.567% ethanol, and then 71% H2O. Now, a little operation that we could do, that's why we have this right here, the vapor flow rate, the vent rate, overhead rate, whichever we wish to call it. We're going to be making an alteration to this to see how we can hit a good balance, to see how we can take out the H2O, the little H2O we have down here at the bottom, to see how we could push it up to spike up the quantity of water. We're currently at 71%, and remember we're supposed to predominantly have water here. We have water. We wouldn't say predominantly, but we do have water here. So let's see if we could improve the quantity. So that's normally for the alteration, you go up and down to see which one favors you more. So let's start with going up, and the increments are supposed to be gradual. The alteration, we're currently on 25,000. We wouldn't want to jump up to somewhere around 30,000 in one alteration, because that might make our column to be messed up to unconverge, and in the worst case scenario, it might permanently mess up our parameters, and we would need to delete the column and drop a new column and do new configurations and come down here. That's a lot of work. It's painstaking. So we will approach this gently. From 25,000, we will be going to 27,000. 27,000, and as you can see, our H2O dropped, and that's not what we want. We want more H2O at the bottom and more ethanol at the top. So we're going to be going lower instead of higher in terms of the alteration. So let's go back to 25,000, and you can see the H2O increased. Let's go 23,000. H2O is increasing. Let's go 20,000. H2O increasing, but the ethanol is reducing, and the H2O is increasing. So let's go 19,000. Let's go 17,000. And then we have 94% H2O and 99.9% ethanol purity. Let's go lower. Let's go 15,000. And then we have 99% H2O and 91% and 8% ethanol purity. Well, we need to work on that. We're actually on 1,500 and not 15,000. Let's correct that. 15,000. Much better. 89% purity of ethanol. We have 89% ethanol in the ethanol stream, and then we have 10% H2 in terms of quantity. So that's too much. Remember, we said we cannot have 100%, but then we can have a purity percentage of 89, 90, 95. Let's go back to 17,000. It looked much better. 17,000. Yeah, much better. 99.9% purity of ethanol. And then for the water purity, you have 94%. Let's make it balance up. A bit more. But then remember, it depends on what you're more interested in. In a scenario where you're trying to separate ethanol and water, in most cases, you'd be interested in the ethanol component than the water. But then if you're more interested in the ethanol component than the water, with this, you would say that you have a good separation if you're more interested in the ethanol. So it comes down to what you're interested in. If you're more interested in the H2, you would do better. You would try and alter it. Let's try and alter that. Let's go 10,000. Hope the column does not converge. Yeah. And we have 96% H2 purity. Let's go lower. Let's go 7,000. 7,000. We have 97%. Let's go 5,000. Column, please don't converge. We have 98% purity of H2O, and then 29% purity for the ethanol. But then we still have some quantity of H2O at the top. With the ethanol, it's predominant at the bottom and at the top, so it's not that good of a separation. That's why we said the column is one of the most complex equipment to deal with. It's painstaking operating it. It takes time, precision, research, and correct decision making. Let's go 15,000. So we have 95% and 10% at the top. With this, you could say we have a good amount of water. We have extracted a good amount of water. Let's go 17,000. 94%. It's dropping. So if you're trying to find a balance, I think this would be a good point to find a balance. 17,000, where we have 99.9% H2 and 0 predominantly ethanol inside the ethanol stream, which is desired, and then we have 94% H2 inside the H2 stream, which is a good amount, and then only 5.7% ethanol inside the H2 stream. So a little bit of our ethanol inside the stream. With that, I think that's a good recovery amount. But then if we were to use the particular formula, we would have a better understanding and a better result in terms of knowing the actual recovery. So with an observation, the recovery rates here inside the performance gives us a good idea about how much we were able to recover, but not the exact amount. So the calculation, the particular formula used to know the amount is better off for actually finding out the exact amount of water you have recovered initially, and you were expected to make a comparison between the product and the feed to know the amount of water entered and the amount of water that comes out, to see how much they tally, how far apart are they. If the water that entered is equal to the water that came out, you could actually say that you have successfully extracted all the water. But remember, in a normal distillation operation, it is not possible to have 100% separation of your water from your ethanol, to have 100% ethanol at the top and 100% water at the bottom. With the normal distillation operation, it is not possible, but we were able to hit 94% for H2O. We were able to extract 94% and have about 5.7% ethanol at the bottom. And for the top, we're able to do a very good job and have 99.9% ethanol and 0.005 H2 at the top with it. So let's go back and look at it from the perspective of fractions, mass fractions. We have 88% mass fraction and 11% 11.76% H2 in terms of the fractions present. And for the H2, we still have 100% H2 down here. In terms of mass fraction, we know mass fraction for the ethanol, but then in terms of quantity, we have a little of the ethanol present. So with this, remember what we said? You head to the design, click on the specs, and you make the alteration to have a better purity result. But then, and you head to the performance to know your recovery rate. But bear in mind that the recovery, using the recovery function, doesn't give you the exact, it's more like an estimate. It doesn't give you the exact amount of recovery. So you need to use the formula, and we will be looking at the formula extensively in our intermediate course. With this, I believe we can say we have successfully operated the distillation column, and we have reached the end of our content, and not just the end of our content, but also the end of the beginner's journey. And if you followed us down this far from the beginning, like I'm not just talking about today's content, the beginning of today's content, the beginning of the beginner's journey, congratulations, you have now graduated as a beginner in Aspen Hysys with the equipment we dealt with, of course, but they were a handful, and you are about to become an intermediate in process engineering, design, and operation. Congratulations once again, and we look forward to seeing you in the intermediate course. Thank you very much.